It's a privilege to have Urs join us today as part of this lectureship series. Data center efficiency is a growing and important area of research. He is the pioneer, the father, the progenitor of this research. Today he's going to be speaking about its convergence with machine learning and cloud computing technologies as a way of reducing IT energy consumption. Please join me in welcoming Dr. Urs Holzle.
Thank you. Thank you. All right, you're giving me too much credit, but indeed, let me just see how I advance slides here. All right. Indeed, I want to talk today about a number of different things, and I'm kind of starting with the assumption that not everyone knows exactly how data centers and actually energy look like, and so I'm going to go from the buildings and the high-level picture to the servers, to the actually electronics, and then hopefully put it together afterwards. And the reason I picked this topic tonight is that it's relevant for a number of different reasons, right? So as Google, we run a large compute infrastructure, and the power bill for that compute infrastructure is many hundreds of millions of dollars a year. And so you clearly want to spend less, right? So energy efficiency matters. But the second reason is, and that's what I wrote, I think, in the abstract, is that the IT industry overall, so not cloud computing data centers, but everything, right? Every data center, server closets, desktops, routers, the whole thing, uses roughly as much energy as, or produces as much carbon as the airline industry, right? So it is actually pretty high up on the map of things, about 2% of global carbon footprint. So it matters that we figure out how we can reduce that. So let me start with the building level. A data center basically is a building where electricity goes in and heat comes out. And sort of as a side effect, it does web search or Gmail or YouTube or other kind of things, right? But really from a physics perspective, heat goes in and power goes in and heat comes out. 191 terawatt hours. I was too lazy to find a newer number. This was a few years ago, but it's pretty much similar today, is the total amount of energy, electricity used by just servers. So that's not the whole IT industry. This is just servers, right? Terawatt, you should know, large number. So that definitely is a significant impact globally, right? Again, for comparison here, Mexico would be roughly the same amount of electricity consumption. Right? So it's really a very meaningful amount of power. For comparison, Google uses about as much power as the city of San Francisco right now. So these two are kind of within 10-20% of each thing, right? Which is a lot, right? San Francisco is a meaningfully large city, like 800,000-900,000 inhabitants. At the same time, it's not very much when you think about the 2+ billion users that Google serves, right? And so if you translate that into sort of per user consumption, it's actually very little, on the order of less than half a watt, sort of continuously per user is what's used by all Google services combined, so including YouTube and Android, push notifications and search and Gmail and Google Cloud and everything. So how does data center usage look like? This graph here is from a DOE study that was updated, originally done 2008 and updated, I think, 2013. You can see here a number of different trends. The top graph, the line at the top, is what they produced what they forecast in the previous report in 2007 or 2008, right? And fortunately, that curve did not happen, right? What happened was the black curve. And the difference really is that a lot of the growth in data centers was in very large data centers like Google's data centers. And these data centers are actually much more efficiently run than the average data center. And I'll talk a little bit about that. So you can see it's actually been, in the US, relatively flat. Globally, it's been slightly increasing. Here's where the energy goes in a data center. So let's focus on the left first. This is kind of a typical, not very good data center, but actually very average data center. So this is not constructed to be bad. This is actually pretty typical, right? So from the top, about a third of the energy goes to mechanical cooling. So this is kind of like what's in your fridge. So large chillers, they take some cooling medium and make it cold again, and then send it to the servers where it gets warmed up and it gets cooled again. CRAC is computer room air conditioning. So this is basically the thing that sits on the floor and translates the cool water into airflow. IT equipment is what you actually want to run. And then PDUs, power distribution units, UPS, uninterruptible power supply, so the backup power, right? So the shocking thing here, and this is really very typical of I bet that UCSB has a server room that looks exactly like this, right? So it's not made up, this is actually relatively average, right? So the shocking thing here is that IT equipment, so your actual load, is a minority of the energy consumption, right? Everything else goes somewhere else, right? Just to keep the servers alive, so to speak. Right? And that's what actually led to this curve that you saw in the first graph, right? Because every new server gets multiplied by 3 for all of this overhead. Here's a study of larger data centers that Lawrence Berkeley Labs did, or Lawrence Livermore, I forget which, Lawrence Berkeley Labs. So they looked at larger data centers. So the theory was larger data centers are run more efficiently. And so the average they saw, so they looked at 24 different data centers, and they saw an average of 1.8, right? So a little bit better. So this here is a factor of 3 overhead. Factor of 1.8 overhead means that there's 55% going to the actual IT load and 45% going to other stuff, right? So still, it means every server that you introduce gets multiplied by a factor of 1.8 in terms of the energy consumption, right? Because it's in a data center. Here's another way of looking at it. So the study split it up by sort of different types. Interestingly, the very large and the very small ones are better than the middle. And the reason is actually that the server closet, people actually don't worry about cooling more or less. You know, cooling, you know, if you just have a few servers, then actually kind of air sort of just dissipates and it works. So you don't actually put in air conditioning, so you save a little bit. But sort of the typical server room is 2.5, factor of 2.5, factor of 2, pretty bad. And then their value for hyperscale was 1.2, so 20% overhead. This is a lot better than 80% overhead or than 200% overhead. This is actually what Google does. So this is our average across all the global data centers. That includes places like Singapore, Taiwan, South Carolina, that are actually pretty hot in the summer. So it's not just nice places. This is measured with PUE, power usage effectiveness. That basically is the ratio between the total power that you consume and the actual IT load. So 1 is the best, because 1 means it's really just your server consuming energy and there's 0 overhead, right? So we're running at 1.11, or actually at 1.12, the yearly average. So we have a 12% overhead, right? And that's one reason why this curve has come down, is because if you introduce a server into Google Data Center, there's only 12% overhead for other stuff, mostly cooling, to actually cooling. So that's great, because it means actually you can run these things very efficiently. I don't have time to talk about sort of what's in there, but the answer is actually mostly paying attention to physics, keeping airflows controlled. Don't let cold things mix with hot things, because you spent energy making things cold, so don't waste that energy by mixing it with hot things. Using evaporative cooling, so basically just evaporating air to remove the heat. That's very energetically very efficient, et cetera, et cetera. In fact, we can do better than this, and you'll soon see this line actually drop down a little bit more. Starting about 18 months ago, we tried to see if machine learning applied to the cooling control system would help. And the answer is actually it does. And here's how it looks like. So this is the overhead, so the PUE basically over short periods, so minutes. And then at a point where you can clearly see, we turn on the machine learning control of the building, and then we ran it for a while, and then we turned it off again. And you can see there actually is quite a significant savings. So what is happening here, right? So what's happening is that we took a building and fed all its parameters into the cloud, machine learning. And so you see every few seconds or whatever, what is the pump speed, what is the fan speed, what is the outside temperature, what is the load on the data center floor, et cetera, et cetera. And of course also all the overhead, all the energy metrics, right? So the machine learning system as inputs had a lot of data points that were just historic for that building, plus what the cooling overhead was, right? And then you train it to find the lowest the settings that produce the lowest cooling overhead. And the reason why it is so efficient is essentially that it produced a control system that is very, very specialized to just that building, right? So physics is still physics, right? Like you can't actually do cooling cheaper. But what happens is that sometimes the building, let's say, is partially loaded. And let's say you have 10 cooling towers and you need to run only 3 of them. Let's say each cooling tower can remove a megawatt of heat, right? You only have 3 megawatts of load. So what do, right? You could run all 10 at 30% load, or you could run 3 of them at 100% load, or you could run 5 of them at 60% load, right? All of that removes 3 megawatts of heat, but which one is more efficient, right? And also, you could run this one, and that one, and that one, or you could run this one, and this one, and this one. And the machine learning system basically picks up all the peculiarities of the building and realizes that, for example, that this building compared to other buildings maybe has more thermal mass in its pipe system, so that when you have an excursion, you actually don't need to turn on cooling because you know it will basically disappear just as water flows through the pipes, right? And so you avoided turning on a cooling unit and then turning it off a few minutes later, right? Theoretically, you could do all of that by hand. But you would have to observe the building very closely, and you'd have spent many, many hours of custom, writing these control loops. And by the time you're done, someone probably changed the building, and someone certainly changed the load in the building, and so your control system is no longer optimal. But machine learning lets you kind of follow that curve and just figure out something that's pretty esoteric, right? And so the system occasionally does really weird things in terms of how it sets pumps, or not weird things. So you can explain it, but it's not something that an operator would do. Right? And last but not least, this is all in as a baseline of something where the local team manually actually has been trying for several years to run this data center very efficiently, right? Because they're proud of the efficiency that they reach, right? They're proud of being 11%, where the average world is at 80%. So this is a hard place to start. We didn't think that we would see this at all because the team is actually doing a good job. Last caveat, this is only in the summer. In the winter, you don't see that, because in the winter, when you're in a cold location, basically you spend so little on cooling. Like, it just works, basically, and one cooling tower is on, and the pumps are at lowest speed. And, it's cold outside, so everything just works, so you can't really save much there. But very excited about that, and you see our curve, our worldwide average. We're now introducing this in all the buildings. We're going to see that drop by another, 10% or something like that. All right, so just to recap what you learned so far, a lot of energy used by data centers in aggregate. And again, by data centers, don't just think of the big ones, like the ones Google run, but actually server rooms, a little bit larger rooms, enterprise data centers, et cetera, the whole thing. Small is bad, large is good, and it's really mostly because at the large scale, it pays attention to, pay people to really work hard on it, right? Design it well and work hard on it, because you amortize all that effort. 10% overhead is kind of what you can get. With machine learning, we maybe could get that down to 9% or 8% or so. So that's kind of as far as the buildings go, right? So we now know that if you put a servers in a building, there's a tax, sales tax, so to speak, energy tax of 8, 9, 10% on top of it. But so how do we make the server energy go down? Well, servers is actually a totally different area, but interestingly, it went through sort of a similar evolution. I'm not going to show it in as much detail over the last 15 years. So 15 years ago, if you looked at your average server, roughly half of the power of that server kind of disappeared into stupid places before it actually reached the CPU and the RAM and the disk. right? So the average server used twice as much energy as it should have because the power supply was inefficient. It had multiple voltages. The voltage converters were not efficient. The fans were too big, et cetera, right? What happened in computers that was, that people started to notice that, and also with the introduction of mobile, laptops, et cetera, suddenly efficiency was actually a design criteria. Before, basically, users of servers were not asking about the energy bill. Often it was actually a different department that paid the energy bill, so the buyers really didn't care. But if you buy a laptop, you care about battery life. If you have an inefficient laptop, then the same battery lasts less time, right? So people started to pay attention to all these overheads, and as a result, those overheads, similar to data center, but really from a completely different angle, came down from something like a factor of 2 to, again, something like 10% overhead. So today, if you look at a modern server in a Google data center, and it gets 110 watts, then 100 watts of that actually is useful for computation. And the rest is basically energy conversion, voltage conversion, and a fan. All right. So the overhead is the DC conversion and the fans, right? So as the last thing, inside the motherboard, actually things run at different voltages. And a CPU, for example, runs at about 1 volt, roughly operating frequency. The thing that comes in our servers is 48 volts, so you have to translate that down. And it's pretty efficient, but you lose a few percent. So that's where we are. Now, more important, actually, over that time period was how much energy do you use to do a certain computation, right? So the improvement in the same 15 years of energy used to do a certain amount of computation probably was, I'm guessing, a factor of 25 or more, right? Why? Moore's law, right? Computers get faster every 18 months. The Moore's law used to say they get twice as fast every 18 months, or you have twice as many transistors as every 18 months. And so over time, that really makes the same 100 watts do much, much more computation. Unfortunately, in recent years, that trend has really flattened out, and it's flattening out further. So that's the end of Moore's law, or actually more exactly, Dennard scaling. Dennard scaling is how the circuits actually cause Moore's law, so to speak. So circuits are very hard to shrink these times. They have leakage current. They have other physics effects that really push you to the boundary of things. And so right now, Moore's law is probably down to something like 20% every year, right? So every year you only get 20% speed up, right? Still pretty good, right? Compared to what you can do at a data center. Like, we'll never get a 20% improvement in the data center efficiency because we're at 11%, so there's not much to go. So pretty good, right? Moore's law. So every year, as computers get a little bit better, you get more energy efficiency, right? One of the ways that you get additional energy efficiency is this thing called clock gating or dark silicon. So the idea there is that you have a CPU, and that has maybe tens of billions of transistors on it today. But in this particular cycle, maybe you're not doing any floating point computations, right? So there's no reason to keep the floating point unit powered up for that cycle, right? So at a very fine granularity, the CPU is turning off circuits that are not used right now, just really for microseconds. So that, of course, saves power as well. We have the same thing for frequency scaling. So when your computer isn't as busy, it actually runs at a lower frequency, and that uses less power. So as your laptop, you're just staring at the screen and typing. Your computer really needs to wake up. If you're a really fast typist, wake up 10 times a second to kind of receive your keystroke and put it on screen. And the rest of the time, it's just sitting there waiting. So the clock actually goes down to a much slower clock. Your computer actually becomes much slower because it has nothing to do, right? So that saves money as well, and energy, and then specialization. Now, I'll talk about the last two in a little bit more detail. Okay, so here's a graph, a little bit complicated, but x-axis is time, and the y-axis is the energy proportionality. Here, measured as how much energy does the computer system use when it's running at 10% utilization. So you take a server, And these servers are from a public benchmark database. So you take a server, you're running at 10% utilization, and you just measure how much power it draws. And then you compare it, how much power it draws at 100% utilization. And you see that back in 2007, we start in a pretty bad place, right? The server's running at 10% utilization, yet it uses 60, 70% of peak power. That means its power draw is not very proportional to the amount of computation it's actually doing. Right? It's kind of a bad property because actually servers aren't always fully busy. And this says even when you're totally idle, you can't really save much power because you're still using 60%, 70% of the full power. Right? Nice thing is that servers have become much more energy proportional. And so now over here, we're actually pretty close to 10%. Right? So that means when the server's running only at 10% load, it's actually using 10% of the max energy. Right? That's good. Right? That means if you can control utilization, you also control energy much more. So that's called energy proportionality. And actually lots of companies, including Intel, et cetera, have spent lots of time getting there. And clock gating that I mentioned before is actually one of the ways how this works, right? And frequency scaling. Right? So that's very, very useful because in a typical data center, even in a well-run data centers, the average utilization is more around 50, 60%, not 100%. Makes sense, you know, at peak day, and you know, versus 3 a.m., the load is just not the same. In a typical enterprise data center, by the way, the average utilization is more like between 10 and 15%, so it's actually very bad, right? And that's where this matters even more for energy usage. Here's the second reason why energy consumption goes down, and that's specialization. This here is a machine that we built that is for machine learning computations, so TensorFlow computations. It's called Cloud TPU, and it has 11.5 petaflops of operations. So petaflops, floating point operations per second. Uses less than 200 kilowatts. If you look at the, and it would be today, it would be the 8th fastest computer on the list of on the top 500 list of supercomputers. Right? If you look at number 8, or everyone sort of above, they use typically about 2.5 megawatts or something like that. So more than 10 times more power, right? Why is that? Well, this computer is built purely for machine learning. It cannot do weather simulations. It's not actually a supercomputer, right? It's a supercomputer for machine learning, but it's not a general purpose supercomputer. And so it turns out for machine learning, the floating point calculations you do can be very low precision. Right? And therefore, the energy used per multiplication, per division, per matrix multiply is much, much smaller than a supercomputer. So this doesn't have better electronics than the supercomputers on the top 500 list. It does much less work per flop. Right? It's a specialized hardware, which means we can afford to do 10 petaflops of computation for the purpose of machine learning at a price of 200 kilowatts instead of a price of 2 megawatts. Right? So it's very, very important if you do a lot of machine learning and no weather forecasting. And that's what we do. Right? And so you see that in other places too, where people are starting to do specialized chips. Right? So this has ASICs, application-specific ICs, that are built just for this application, right? Just for machine learning computations. Right? And that makes it literally a factor of 10 more efficient. And you see that in other places. You have that in your phone. Right? Your phone actually has some form of GPU that is, optimized for, drawing games on your phone or something like that. Uses much less energy than the CPU, and therefore has a longer battery life. So specialization is actually one of the most powerful instruments there. Okay, so to summarize servers, obviously that's what actually uses the energy, and the data center overhead is on top. It's still improving quite a bit. So if you have a server, then typically, let's say 4 years later, you have a server that uses much less energy to do the same amount of computation. So you tend to actually throw away the existing server. So you still have a fair bit of improvement, certainly much more than the improvement in physics around the data center. We have specialization that really helps energy efficiency. And I didn't talk about it as much, but all of these things actually are most efficient when you actually use them, right? It's very hard to be efficient if you have something sitting there that doesn't do something useful, right? All right, so back to the carbon footprint, right? So if you take the servers together and the data centers together, you get energy. From energy, you get carbon footprint, right? Here's a picture that I mentioned in the beginning. The IT industry overall, data center is only a fraction of it, but the IT industry overall uses about 2% of the world's energy, right? Happens to be as much as airlines. Unlike airlines, the IT industry actually can be used to address energy efficiency in other areas, right? So for example, the building controls in this building here count as IT industry, but they clearly save, if properly programmed, they save energy in the building, right? So you could argue that the IT industry as a whole has a negative carbon footprint, right? Because the useful things that you do with IT avoid carbon in other places. But in this talk here, I'm only going to talk about the direct footprint of the IT industry. So I'm going to ignore any good things that come out of IT. And that actually is quite meaningful. For example, there's studies showing that video conferencing has reduced business air travel because you can actually, have a video conference instead of physically going there. So let's look at a few forecasts. They're all from the Department of Energy, so they're all US specific. Here's a number of servers installed. And you can see that the only growing pie is basically cloud computing, so hyperscale data centers. Here's the energy from those servers. And you can say it's actually relatively flat. The hyperscale becomes bigger, but it pushes down the others because they get retired and replaced. Some of them get replaced with a hyperscale servers instead, which are more efficient. And here's the more abstracted forecast. And the top curve is basically what you saw. The top curve is current trend. So what would happen if nothing changes? So things stay relatively flat, which is good, right? Which is good that they stay relatively flat. But the one I want to point out is one is BP, best practices. That is a hypothetical scenario that says, what if everyone ran their data centers as well as the hyperscalers and had a PUE of 1.2? Right? Never going to happen. Like guaranteed never going to happen, because it means every single server closet, server room, data center everywhere, would be run as efficiently as Google runs its data center. It's actually not economically possible, and also training-wise, et cetera. Never going to happen. But that would really depress the energy usage quite a bit. Right? The other curve that's interesting is hyperscale shift. They're basically assuming that some of those workloads get shut down in an on-premise data center and then move to the cloud into a hyperscale data center. And obviously, they get replaced with a more efficient server and a more efficient data center, and therefore total energy usage go down. And you can see here that the impact actually could be quite significant. Right? So in this scenario here, the combined reduction would be about 50% between best practices and hyperscale. Best practice, again, never going to happen. So let's look at just hyperscale. Is still about a 25% decrease of total energy in the data center market. And I'm here actually to tell you that this is wrong. Right? They're really underestimating how much energy will decrease in the with cloud computing. And so in the rest of these slides, I'll talk about why I think that is the case. So here's an example, actually, from a study that we did, extrapolated to just basically email servers and SharePoint servers. Right? So we had a customer. So we sell Gmail to companies and to the government. So we had the General Services Administration, a US government agency. They moved from an on-premise email system to Gmail. And and actually the DOE, if I remember correctly, the DOE was together. We did a study to really measure what did that workload consume in power when it was still on-premise, and what did it consume once it was in Gmail. The result there of that particular study was a 93% reduction in energy from the old email solution to the new email solution, right? And at first we were actually kind of shocked how big it was, and we really had tuned every assumption to the pessimistic side, and we're still 93%. So how can that happen? The reason, or the way it can happen, is actually a number of ways, and they're actually fairly typical. So let me walk through an email example, but this is really just a template for many, right? So suppose you're running email for this building. Let's suppose this building was a company. You're the system administrators. You're running an email server, right? Well, so you have a server, right? The vendor probably sold you a server that's a little bit too big compared to what you actually need because they make more money and you didn't exactly know and you didn't want to take a risk, so you bought that server, right? So during the daytime, maybe it's somewhat utilized, right? Maybe you're running at 20% utilization or so, right? And when you bought it, you wanted to last it for a while, so you kind of bought it a little bit bigger. At night, it does nothing, right? Nobody's sending email in your company, so it's kind of idle, right? But moreover, that salesperson reminded you that people really care about email, so you better buy a server and a backup, right? Because what if the server fails? Your company is down, everyone's going to yell at you, right? You're going to lose your job. Bad idea. Let's have a backup server, right? Well, that means 99.9% of the time, you actually have a second server that is idle, doing nothing, right? So you have a factor of easily 5 overhead versus the best possible system just from that setup, right? And then on top of that, of course, right, you have an AC unit blast cold air on it because you want to be sure that the server doesn't die, et cetera, et cetera. So that's why you have a pretty high overhead system. When you move that to a cloud-hosted service like Gmail, you have millions of people, millions of mailboxes in the same data centers mixed, right? They come from different time zones, so your average utilization is better. We still have the worry that a server dies, right? And so we need a backup. But if you have a pool of 1,000 servers that serve, tens of millions of mailboxes, and you want to be safe, well, you put, let's say, 10 extra ones next to it, right? So 10 servers can die before you have any problem, right? But that's only 1% overhead, right? You have a pool of 1,000, and then you have 10 backups. That's 1% overhead, right? So you can get the same functionality at much, much lower effort. And then on top of that, of course, you're in an efficient building, et cetera, et cetera. So we calculated what this all would mean for just regular Office applications. So your email, your documents, et cetera, right? You would basically save just for the US, you would basically replace or free up the same energy usage as Los Angeles, right? So this alone. Remember, I told you Google uses about as much energy as San Francisco, right? So this alone would save more energy than 10 San Franciscos, right? Los Angeles is easily 10 times bigger than San Francisco, right? Just from adopting Gmail everywhere, right? So that means that this compression factor, if people actually shut down their email servers, right, one by one, and actually replace it with something like Gmail, then the compression in the energy usage is really enormous, right? It's not just the server to server, but actually it goes from 2 servers to a fraction of a server, right? And then on top of that, that server is more efficiently run, et cetera, et cetera. So that's how you can get these very, very high reductions, right? On top of that, you have other factors. Because if you do now more workload in the cloud, your client becomes cheaper because it needs to do less work, right? So today, for pretty much any application, your phone is actually just fine, right? It's fast enough to run email and documents and stuff like that and games, right? The thing that bothers you most is the screen size, right? And maybe the battery life, right? But it's definitely actually your phone is good enough, right? And if your phone is not good enough, a laptop's good enough, right? Well, if you look at what these devices use, this is from National Resource Defense Council, average annual energy usage of the different devices actually happens to line up pretty much with the peak watts that they use when they're fully on. A tablet is easily 25 times more efficient than a desktop, right? And a laptop is somewhere in between. Back then, remember they say notebook. This study isn't quite new. Today, the notebook is probably in a 35 watt, like this A laptop is probably 35 watt or less, a kind of typical energy usage. So again, now if you use mobile clients, because your storage and your compute actually happens in the cloud, you're also reducing energy on the user side, right? And remember the number I mentioned before, right? I said the average server side energy usage of all Google services together is on the average, on the order of half a watt, sort of used continuously, right? Even a laptop here is much more than half a watt, right? So that means actually when you do a Google search, your laptop during the time when you type your search uses way more power than the search actually uses to give you the results, right? So the end user equipment really matters in the equation. All the graphs you saw before were just data centers, right? Just the server side. On top of that, there's an extra factor, namely that the hyperscale data centers use much more renewables than the average data center or the average company. And not everyone's the same, but this year actually we're reaching 100% renewable energy for our data centers and actually also our corporate offices. What that means is that we have created the same number of new megawatt hours of production, renewable energy production, wind, solar, et cetera, than we consume worldwide, right? So we, as Google, we have additional consumption in the world, and we have the same amount of additional renewable energy generation. Here's a brief example. Actually, the picture you saw was from a wind farm in Holland. So here's our projects. Many of them in the U.S. in the wind belt, but there's sun, and we have a data center in Chile, so there's a solar farm in Chile. Lots of them in Europe as well, right? So all of these were built because they're financed by power purchase agreements from Google, right? And so that means, to go back to the previous example, if you move your office workload and your company does not run on renewable power, and you move it to the cloud, not only do you save energy because of all the things we just went through, but then that energy that you use is now renewable, carbon neutral, and so you really actually go to zero, right? And it's much easier for us to do this than for the average company to do that. That's actually a sad state, so let me digress briefly. In the US, unfortunately, where much of our energy usage is, you can't actually buy renewable energy. You can buy it, but you can't use it, right? It sounds kind of paradoxical because, hey, you can put panels on your roof and, doesn't that work? But your panels are behind the meter, right? So if you install solar panels on your house, you're using the energy directly in your house, and they're behind the meter, and so you're just pulling less energy. In a data center, that's not realistic, right? There's not enough area to put solar cells. Plus, the location where the data center is not necessarily the right location for the best sun or the best wind. And so the wind farm is, tens or hundreds of miles away. And in the US, you cannot actually build a wind farm and then connect it to your data center and actually use the energy. That's actually illegal because utilities have a monopoly. You need to take your power from a utility. There is a solution to that. We actually, in the US, Google has become an energy trading company because we buy energy from the wind farm, then we sell it on the open market, and then we buy energy from our energy provider. And yes, right? So we can do that. We can do that as Google. That makes sense for us, right? At our power bill, that makes sense for us. But clearly, regular companies, is too much work. You can't really do that, right? So that's an extra advantage when you move the workload to the cloud. We're not the only ones doing this. Here's an example of, I don't have 2016, of the renewable energy deals done in the US. The numbers on top are gigawatts per year. And this is from corporate buyers, right? So these are only deals not from energy companies that are buying renewable energy, but from corporate buyers, right? So Google shows up here, IKEA, Walmart, Facebook, Microsoft. The 2016 bar is even larger. And so this is increasingly a trend. And pretty much all of the cloud providers have committed to renewable energy, to getting to renewable energy, though most of them are not there yet. right? And so to add that thing, we have under contract about 2.5 gigawatts of renewable power across that world map that you see. That is nameplate, right? Average power that you get out of that is probably more like, something under a gigawatt or so, right? Not all of them are online, because typically when you sign a deal, it gets built, and it takes sort of 18 months to 2 years. That's why it actually took us about 10 years to get from 0 to 100%. All right, we do a few other things. Try to avoid landfill from data centers. In fact, we have our Oklahoma data center was the first one to reach zero waste. So there's a bunch of other environmental benefits. Really, again, they work because in a concentrated place where you have lots of computers, it makes sense to set up a waste recycling program, right? Whereas in your company where you have 50 of them, when they go, then you put them in a trash, or if you recycle them, it's not as efficient, right? So just to recap what I just said, right? So we're roughly about 2 times efficient, just the building. You have really large factors. I'm making this up, right? So it's not exactly 87%, but factors of 2, 3, 4, 5 reduction just by not having server backup, et cetera, et cetera. You have, of course, 100% then of that renewable. So that adds up actually to a lot better savings. And so here you heard this first in this room, and this is my personal position, not Google's official message, right? So I'm telling you here about what I personally believe. But I actually think that this graph that you saw about IT energy usage, not just data center energy usage, but actually IT end-to-end, right? All of IT will reduce by a factor of 2 in the next 10 years, right? Meaning it will go from 2% to 1%, right? And on top of that, if you look at a carbon footprint, it will go even further, because the hyperscale fraction of that, which at that point probably will be 50% or so, will be carbon neutral, right? Will be powered by renewable energy, right? Hopefully some of the other part too, but I'm just speaking here for the industry, right? Meaning that I'm actually pretty optimistic that all of those curves that the DOE points are far too pessimistic, right? Because A, they're just looking at the server side, they're ignoring the renewable factor that's really coupled with load growth, and then they're also ignoring the mobile client thing. You should, if you paid attention, you should know that I kind of waved my hands at certain times. I'm actually omitting a few factors that can throw a wrench in this. One of those factors is the energy usage of networks, right? Like if you have a mobile client, well, you need Wi-Fi, right? Your Wi-Fi hub uses about 10 watts, right? And then it goes to an Ethernet switch that probably uses another 5 watts per port, and blah, blah, blah. Cell towers actually use a fair amount of energy for your mobile devices, et cetera. But it's less studied how much energy is in that field, and also it's less clear whether moving your server from on-premise to the cloud changes that network pattern at all, right? Because probably you were still using your phone to access your email, even if it's on a server on premise, or you're still on Wi-Fi with your laptop. And so I think that is actually not affected by this move to the cloud, and I'm not sure that it's going to drive more bandwidth, so to speak. All right, so just to repeat, cloud data centers, they're more efficient, so moving things to the cloud will be better. The applications run much more efficiently just because of scale. Gmail can get by with 1% redundancy, whereas if you do it yourself, you really kind of need 2x redundancy. It allows mobile clients, because all the heavy lifting works off-site. If you have photos on your phone with Google Photos, you don't actually need storage for all the photos, because your phone is really just a cache. And then last but not least, all of this, for the hyperscale providers at least, will eventually be powered by 100% renewable energy, and at Google that's already the case. So with this, I hope that you are as optimistic as I am. Also, I hope that you're actually as energized, if you pardon the pun, about the opportunities that we really have as computer scientists, as engineers, to contribute to this curve that goes down, because a lot of energy today is spent without benefit because the control systems, the management systems that actually steer it are just not very good, right? And there's a number of studies that show that in the US alone, you could eliminate 10% of total energy usage, total energy footprint, just from making buildings more efficient, and not by reconstruction, but by making the control systems actually work, right? And so the work that we did on the data centers at least suggests that even at a very well-run environment, you can get very significant savings automatically with machine learning. So with that, thanks very much for listening, and we can get to questions.
Perfect. Thank you, Urs. Okay, so we have some time for some questions. Please come up and use the microphone so that the people who will be enjoying this virtually using 100% renewable energy from the cloud will be able to hear your question as well.
Hi. This is an oddball question, but I'll ask it. Would it make sense to move the data centers to the real cloud in the space?
Yes. So I could play you a YouTube video, actually, because, and I think that was posted on April 1st last year, and where we actually explained that we are the only real cloud, the actual cloud that actually computes in the cloud. The answer is probably not, and the reason is actually mundane. The reason is that data centers are not static things. They actually have literally truckloads of stuff arriving and leaving every single day. And so you install new servers, new disks, et cetera, you move stuff. And if you have something that was in space where the attraction would be that like solar energy is very good, right? It's just too expensive to get it up there. And then once it's up there, you can't touch it, right? And actually stuff breaks, et cetera. That's number one. Number two, connectivity over wireless is still not great. Like satellite to, it's a few gigabits per satellite, and these things have terabits coming out of them, so they that doesn't match as well, right? I think people actually have played with the idea of having data centers in the water, so like underwater, right? The attraction there is that water is a great way to remove heat, and I think for maintaining the fiber connectivity is a little bit easier. If you're not too far away from the shore, you can just pull fiber. The maintenance part is really still the hard part. We have done something that is close to that. A few of our data centers, like the one in Finland, sit right next to the water, and they actually are cooled with salt water that flows through the facility from the ocean, then gets mixed before it goes out with cold water again, so that there's like a 1 degree heat increase as it flows out in the Gulf. And like up in Finland, works beautifully because the water is never warm, guaranteed, but that limits you to places that have these properties, and there aren't that many of them. And like in Singapore, that doesn't work because A, the water is pretty warm, and B, there is no beachfront property left to build a data center. And if there was, we couldn't afford it, right? Because someone else pays more for it. Yes?
So thank you for your informative presentation. So actually, I'm second year PhD, and I'm advised by Chandra and Rich. Mm-hmm. So first of all, I want to thank you for hiring them.
My condolences.
Yeah, that's right. So your decision indirectly affect my admitted career path years after. All right. So I want to ask a machine learning question. So yesterday, I think DeepMind team published a paper on Nature about the AlphaGo 0. Yep. So this kind of equivalent to AlphaGo, but without any human data inputs. Mm-hmm. So they do unsupervised learning and be the original AlphaGo, yes. Right? Yeah, yeah. 100 and 0. Yep. So I'm just wondering, do you consider this could be another singularity in the machine learning community, and also for energy efficiency, because you don't have to train your model yep. for a long time?
Yes, great question. Yep. So for background, for those not as much into ML, so yesterday a paper came out from DeepMind, which is a Google research unit in the UK. And you've probably heard of AlphaGo, the Go system that beat the world champion. So that Go system was trained on something like 100,000 human games. And so that was the initial system, and then it played against itself and got better. So now the new paper is about basically a very similar system, but that never saw a human play. So it started with zero knowledge. The only Go knowledge it has is what's a legal move, and nothing else. Like no heuristics, no nothing, right? And it just basically played against itself, and then saw which random version won, and then adjusted the weights, et cetera, and it became a better bridge play, Go playing. My wife plays bridge, so a Go playing program than the original one, right? With zero knowledge, right? Now that's amazing that you can sort of bootstrap out of nothing, like really just knowing the rules of bridge into a program that beats any human by a mile. Like, so it beat the AlphaGo version, which won against Lee Sedol 4-1. It beat that by 100-0, right? So like it's way the best player in the world, right? That's amazing. I don't think it's a generalizable thing yet, because the nice thing about games is that you can have a perfect simulation of reality. Like that system played millions of games against itself. These games were exactly right. Like they were exactly Go games because all the rules were observed, and so they're as good as a real Go game. Here, in a data center, you can't do that because it means we would have to build a perfect physics model of the data center, right? That perfectly mimics what happens if you run this pump a little bit faster, right? We could, too expensive, right? However, to some extent, the cooling system is a zero-knowledge system as well because it knows nothing about the data center, right? Literally, all it knows is that here's 200 different dials that you can turn. It doesn't even know that this is a pump and this is a fan. And then it knows this is what happens to the overhead, right? And here's what happened a year, like people randomly making changes or actually the weather changing. And it doesn't know anything else. And from that, it learns how to control those knobs, right? So it's actually kind of similar. But I wouldn't call it a singularity because, again, here you have a system where inputs and goal function are exactly measurable. And you have an already existing system that you can just observe. But the power, actually, of this machine learning is not that. The power is, or the power really is that you get a very specialized system for this building at almost zero cost, like just by training. Which means you can do it for every single building, and you will just learn the peculiarities of this building. Let's say for this building, you would learn that the sun shows up at 10:30 in August, right? But not in January. And you would not have to program anything about sun at all, right? It's just something that happens in the variables, and you just train on it, and if you have time as an input, if you have outside temperature as an input, if you have all the dials of the various fans, it will hopefully do the right thing, right? And the amazing thing to me is that this worked for data centers. Actually, just as amazing, actually, almost more amazing that it works than for Go for me, right? DeepMind actually helped us with that too. They're very, very similar, so there's a little bit of similarity. But I think the singularity, so to speak, when our computer's smarter than humans is actually far, far away, right? Because we tend to overestimate by saying, oh, Go is really hard, like I can't play Go, so this thing must really be amazing. But it's very, very narrow and actually very brittle. And so as a last thing, you see that with image recognition, right? Image recognition is insanely good, but you can modify, a relatively small number of pixels in an image of a zebra, and to you and me, it's clearly still a zebra, but the algorithm says race car, 99% certainty. Right? And that kind of shows you that it's actually still not a very robust representation of what a zebra is. It's a very brittle one, right? Works amazingly well because images are not random, but it's not actually quite, like it's not getting at the essence, right, of what a zebra is, right? And that, I think, is what's standing between that and sort of more general intelligence. And whether we overcome that or not, not next year, I would say. Ray Kurzweil says 2027, I think. Who knows? Yes. Next question, yes.
On this side.
Oh, sorry, yes.
I was curious, you didn't break out your storage farm. I mean, and I'm curious about why you didn't do that, and also, a transition to solid state, and are you using machine learning in storage?
Yeah, good question. So storage is the same as server for us, right? So some servers have disks and some servers don't, and they're all connected by the network, so it's kind of all the same, right? You're actually right that a fair number of the cubic inches, so to speak, in the data center slots are actually filled by disks, not by compute. And that's just because disks are actually relatively chunky kind of systems today. You have 10, 12 terabytes, and it's still, a 3.5 inch by, 1 inch by whatever, right? Transition to solid state is definitely ongoing. It's still a lot more expensive per gigabyte, but obviously the access is much, much faster. We use machine learning actually in quite a number of different places because more or less our belief is, and we're not really fully through, but our belief is that any system that is a tuning parameter, this tuning parameter should not be set by hand. Right? It should be set by an algorithm, and most likely by a machine learning trained algorithm that just observes, how much should you put in flash, right? What's the total system cost, what's access speed, et cetera, and then basically creates, actually something better than a heuristic. And it actually, in the places where we've done, works really well. And the reason really is that when you do a heuristic, you try to be general. And that actually is a good idea, makes it robust, but it misses the special cases, right? And the machine learning system, if you have a large application that is actually kind of weird, actually creates a heuristic just for that application, that weird application that really does something unintuitive, but that makes this application work really well. And if this application disappears, it just trains itself on the next thing that comes along. So you don't have to pay. If you do that by hand, then you actually put in weirdness, then it becomes brittle, and when the weirdness changes, suddenly your thing blows up. But the machine learning system actually continually kind of adapts and gets that right. And so you can kind of explore the weird cases and do really, really well in them. That's actually what happened with cooling as well. At the same time, you still have a stable system that's pretty robust against evolution, right? And doesn't need manual maintenance to keep running. Right? Maybe we'll alternate. Yeah.
So your comment was that you want to make basically the biggest server to make it more efficient, but as the amount of data that's going to be transported increases and energy per bit actually becomes a limiting factor, do you think that's still true, or you want to make like smaller nodes somewhere closer to reduce the transfer of data around?
Photonics is actually pretty energy efficient and pretty distance insensitive, right, to a first degree. And so I don't actually think edge computing is going to work very well because the economics are really just very bad compared to a more concentrated one. And the number of applications that really need it are relatively small. But the other thing that's going to happen is that if Moore's law really dies, then that is going to depress demand as well, right? Like today, if you buy a new phone 2 years later, that phone makes higher res pictures, right? It has more local storage, blah, 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 et cetera. Makes HD or 4K videos, right? All of that generates more demand for processing, for storage, right? If Moore's law ends, there is no 8K after 4K, right? And 10 years later, you still have a 4K video, right? Which means the amount of video that you produce isn't really going up that much, which means on a data center, the demand, the compute also doesn't need to improve a little as much, right? So there's a little bit of balance. The second thing is, the truth is that today we probably waste, 90% of computation in software overhead that doesn't need to exist, right? Today it's not economically actually rational to address that because the compute is cheaper than the developer. But if the compute no longer gets cheaper and your problem gets bigger, it actually pays to say, well, I'm going to optimize this thing. And the server doesn't get faster, but the application gets faster. So I think we have quite a bit to go until that bites us. Yes?
Hi. I have two questions. Do you mind? So my first question was, there was a slide that near the end that you kind of glossed over, but it was a like stacked bar chart of like, was it like energy sales or whatever?
Yeah.
Would you mind explaining that a little bit more?
Yes. So this last 2010 to 2015, the y-axis is gigawatts. So the number at top shows you how many gigawatts were bought by corporate buyers, so by companies, right? And then the stack is just the different deals. We were the only ones in the first 3 years, right? So this was our first Renewables deal in 2010, et cetera. And then, over here, Apple did some small deals, Facebook did one, right? Mars, et cetera, et cetera. So that's the total amount of renewable energy that was really directly purchased by corporate buyers bypassing the utility, right? So that's what this graph is, right? And so the stack up is just the different companies that add up to, 3 gigawatts in 2015.
And my second question was, I've heard that Google uses custom hardware in their data centers. So you mentioned one which was ASICs for machine learning. Do you have any other examples? Or I'm just curious what.
Yeah, there's a few things. So the custom is only recently gone into the ASIC level. Before it was really how you put the parts together. So we have a server that's, for example, one of the things that we have done for a long time is have motherboards powered by DC, not by AC. It's more efficient in the way you do the UPS. And that's now becoming standard, and so it's less custom actually for us. We have some custom CPUs, but they're really built by Intel. So Intel, we're a large buyer, and we say, we actually like what you do, but could you do this a little bit differently to get better throughput or other things? Custom networking gear, but again, many of the chips, almost all of the chips in there are actually chips that come from vendors, right? And sometimes they're a little bit customized for us because we ask for special features. Sometimes they're actually totally off the shelf, but put together in our way. And then the ML chips, we have a few other ASICs, a network chip, for example, a security chip. But the ML machine learning TPU is really the biggest one. That is a really, really massive chip. And that was because we can't cost effectively buy the equivalent in the market yet, right? And maybe 5 years from now we can, and then we'll stop building our own and use off-the-shelf components. Because using off-the-shelf is a very powerful solution, actually, because you can ride a much more mass market audience, and we want to be as much mass market as possible.
Thank you.
Hi, I just had a question about like comparing your solution to like traditional model predictive control solutions like you see in chemical plants and such.
So we still use the traditional control loops. So if you think about our data center, so it has an existing control system in there. So every pump is variable speed and every fan, and it has a PID loop or something else that actually controls it, and the fan, if the cooling tower, spins faster if the water temperature goes up, sort of that kind of thing. What we do is we feed the measurements into the cloud, right, and train on it. And then what comes back is really set points for the local control loop. So actually the control loop is always local, but you change the set points, like how quickly they react to rising water temperature or to dropping pressure or stuff like that, right? So it's really kind of a meta control system, but you could cut the internet link and it will continue to run the building because you're actually using the local control system. And the operations people actually want that because then you can always hit stop, right? And the building is actually in a safe state. You can also hit reset, and then they all go back to their default settings, right? So it's hard to mess things up that way. But we also want it because we don't want to really change the building deeply, right? Like, the control systems is actually physically built into all of these different places. You kind of don't want to ever rip it out because that costs a lot of money. So it's better to kind of coexist with that control loop. But it's really kind of like you changing your thermostat settings all the time, right? Or your AC power all the time. That's what we kind of do. So there's a hand reaching in and turning the dial, but the actual control loop is the old-fashioned control loop.
Thank you. What is Google's incentive to use renewable energy?
Good question. There's commercial incentives, and then there's kind of more philosophical incentives. Commercial incentives, first on the power side, is that the reason why you saw the deals go up like that is because renewable power has become economically viable, right? And one of the nice things about power purchase agreements is that you can buy a fixed price for 10 years. And so today you can buy, in the US, for example, you can buy wind power at order of 3 cents per kilowatt hour, right, or below, like in Texas. So that's very competitive with just regular power, right? 3 cents per kilowatt is actually pretty cheap. So it actually makes sense There's some risk because, power is variable and you need to pay a surcharge in one way or another to compensate for that variability. So it's still a little bit more expensive in the early days of the project, but we think that in a 10-year time frame, we're not going to lose money by buying renewables. So it makes sense economically. Second thing is, it makes sense for us too as a consumer product, right? If you knew that we were using as much energy as San Francisco, and it was, coal power, you might not like Google as much, right? And use our products less, right? So there's definitely a reputation risk. And then last but not least, on the enterprise side too, is actually an extra sales argument. Hey, move to the Google Cloud and you solve one more problem, right, that your company has. You look a little bit better to your shareholders or your users or your employees. And then last but not least, there's a lot of people at Google in the technical staff who are just very passionate actually about environmental issues. And so when these things come together and are doable, they really want to do that, right? Because it's the right thing to do, right? The energy efficiency that I talked about is actually a money-saving measure. Like every time we make the data center less efficient and more efficient, then typically it doesn't cost you that much because it's all in the controls really more than in the rest. And we save on the power bill, right? As I said, we're spending hundreds of millions of dollars a year on paying power bills. So if you get a 10% gain, that's really meaningful. And that justifies having 10 engineers working on the next way to make it cheaper by another percent. Yep.
Okay. So I had a technical question about the machine learning mechanics. So the data sets that you had from just what the operators had done, it was rich enough to allow the machine to learn, or did you guys have to actually do some exploration?
We didn't do anything deliberate, and it is a little bit of a weakness, right? So what the question alludes to is that if you train on a data stream, and that data stream does not cover, for example, very hot days very well, then the predictive power, so to speak, of your model in that area is not very good, right? In the areas of image recognition, you fix that by saying, oh, let me get a few more photos of zebras or whatever where I'm doing badly and label them by hand, and then it gets better. We can't do that as easily. But it turns out that the variability and that was actually why I was skeptical that it would work, but it turns out that the variability is continuous enough, like physics is continuous enough, where even if you don't have that great coverage, it actually works pretty well. And then second one is we always have the exit. I mean, the operator's still there watching things. So if things start to go bonkers somehow, they can just say, push the right button. And
okay, so you do have a sort of an implicit labeling scheme to continue learning
this runs all the time, right? So this also runs now, right? Last but not least, one of the things that we can do, and we did do before deploying, is some input variables are chosen, like the outside temperature and humidity and the load. And so you actually can try some more extreme things, just simulated, right? And see what it does, and make sure that you don't have like wild excursions kind of thing, right? Yes?
I have a question that we know some clouds are distributed, so they have like computing centers all over the world. So is there a kind of strategy or program that can decide which task is assigned to which computing center to save energy?
Yes. So we don't do that for energy reasons. We do that for latency reasons, right? So we have data centers all over the world, and if you're in Europe, you're going to be sent to a European data center, and usually the one that's closest to you. But that's really for latency reasons and not for energy reasons. Generally speaking, it's not viable to transport data over long distances to process it somewhere else, because like a transatlantic cable costs a lot of money and only has a few terabits of bandwidth. So, feeding a few terabits between two racks is really cheap, but between, two continents is pretty expensive. So for energy reasons, we don't do it. Yep.
Hi, I had a sort of generic question.
Mm-hmm.
So when you showed the slide of using ML for, in a data center, I think that the idea was really cool and like very novel. But it's something that was like offbeat, right? So how do you risk running that on a big data center, or how do you like test on smaller levels before you actually deploy it on such a big?
Yes. So we didn't deploy it on day one, right? And like this graph was actually from the first time we deployed it. And the operating team was there with a hand above the button, hand over the button, over the red button, so to speak, right, to turn it off, right? And actually, the very first time it happened, actually, they did turn it off because they thought something was going wrong, right? Because they didn't expect, a 30% drop or something like that. But you can do that actually with testing, like I mentioned before, with simulation. And this is not rolled out to all of our data centers yet, because we have not finished training on some of them. So you just have to be careful. But one of the nice things is that in these larger data centers, it's actually easier to some extent to do these experiments, because like our data center in Iowa is probably, like one building is about 1,000 feet long, and it has these pipes with water. And just the amount of water and thermal mass that is just in the pipe is actually, it's an enormous amount, the BTUs, it's an enormous amount of energy, which means if you actually turn off cooling, then for the first few minutes, just the new water that's coming through the pipe that's still cold actually makes you whole, right? Like not much happens, right? Because you literally have, millions of gallons of water just in the pipe system flowing through the fans, right? So if you don't turn off the pumps, you're actually going to be fine, right? And the pumps are protected by a local control loop that doesn't let you turn them off, basically. So even the ML system cannot actually put things in an unsafe place, right? As I said, the ML system only adjusts the set point of the pumps. It doesn't actually control the pump directly. And so the local pump control still has safety guides, and so it will not go outside of that range. Yeah, so it was actually a relatively safe thing, right? Maybe, do we have more time? You don't? Okay, all right, quick questions.
I was just wondering about the server reliability and failure. Is that loaded into the ML, and what's the time
No, it
scale?
isn't, because it's too noisy. We've published a number of papers of that. The general wisdom was that servers need to be cooled to be reliable. It's not really true. It's kind of a little bit true, but not very strongly. So we run our servers pretty warm. The data center is about 30 degrees Celsius. And so the servers run at like 45-ish, right? And it works fine. And we played with it. And sometimes we see a small effect, but not usually. And so this is a dominant part. And what matters much more is how you locally define the cooling of the tray. So that, for example, like there's baffles that put the air over the DRAM, which is actually the hottest part. And you make sure that the airflow really actually reaches the components that need to be cooled. That actually is more important for reliability.
This will be our last question.
Thank you. Actually, I don't have a question, I have a request. You were talking about saving energy, saving money, efficiency, and all that. Well, have you thought about the garbage dump we have in our oceans, like plastic and all, the Great Pacific Patch, the patch in the ocean? Please do something for that, or have you done something for that? Because it will save millions of lives.
Yes, hey, if we only had like machine learning robots that go and suck up that plastic.
Yeah, do something actually.
It's actually would be doable, but you got to put it somewhere afterwards. I actually think there is a lot of potential for sort of robotic cleanups. In fact, one of the biggest breakthroughs of marine research have been these autonomous vehicles that basically can run themselves for days and weeks, and they come up to surface to recharge, and then they measure all kinds of things, and they literally, and they transmit their data to satellites, et cetera, and that they're autonomous enough that they can basically swim around. We haven't, right? In a data center side, we don't pollute the ocean, right? Because we're too far away from it. Google Earth actually has a team for geo, and they've done a bunch of projects, but it's mostly really about the imaging to kind of see that. I agree with you. It's a pretty big issue, actually, oceans in general, because it's a huge source of food, and it's not in a great shape.
Food only, we are actually living on that. 24% of the oxygen you get from oceans only.
Yes, and carbon sink, and et cetera.
It's a great carbon sink.
Yeah,
do something for it. Right.
Thank you.
Thank you.
So let's thank Urs. It's been a tremendous pleasure. Thank you so much, Urs.
Thank you.